Finally, we get to the last major component that we must add to our solution to approximate blood plasma, and that is carbon dioxide. Carbon dioxide concentration is regulated by the lungs, and in arterial blood under normal physiological conditions, it typically has a partial pressure of about 40 millimeters of mercury, or about 5.3 kilopascals. First, we have the simple fact that dissolved carbon dioxide is in dynamic equilibrium with a notional gas phase of carbon dioxide partial pressure. Next, we recognize two reactions, namely that carbon dioxide reacts with water to form carbonic acid, a reaction catalyzed by carbonic acid anhydrase, and this carbonic acid in turn dissociates into hydrogen ions and bicarbonate ions. Then we have a reaction with carbon dioxide and hydroxyl ions, which also form bicarbonate ion. And finally, bicarbonate ion dissociates into hydrogen ion and carbonate ion. This carbonate ion is not usually discussed in physiological acid-base literature. These 5 reactions have temperature-dependent equilibrium coefficients and can be written mathematically as follows. Dissolved carbon dioxide is directly proportional to carbon dioxide partial pressure, with the SCO2 representing the solubility coefficient, which we previously called alpha in the Henderson-Hasselbalch video. Next, we have carbonic acid in dynamic equilibrium with partial pressure of carbon dioxide. Then, hydrogen ion times bicarbonate ion in dynamic equilibrium with carbonic acid, and dissolved carbon dioxide times hydroxyl ion concentration in equilibrium with bicarbonate ion. Finally, we have hydrogen ion concentration times carbonate ion concentration in equilibrium with bicarbonate ion. Now, the first 4 equations can be grouped into one single representative equation. Hydrogen ion concentration times bicarbonate ion concentration is in equilibrium with partial pressure of CO2, with Kc being the equilibrium coefficient. Note that this is actually nothing more than the non-logarithmic form of the Henderson-Hasselbalch equation. If you were to take negative logs on both sides of this equation, you would end up with the Henderson-Hasselbalch formulation. So carbon dioxide contributes 2 equations, as above. We can then write all the equations for acid-base balance for this simplified model, and there are 6 of them in all. They are hydrogen ion concentration times hydroxyl ion concentration equals K prime W. We've seen that many times before. Then our ubiquitous electrical neutrality equation, but this time with bicarbonate and carbonate ions included as new anions. Then hydrogen ion concentration times A minus concentration to give HA, our weak acid concentration. HA concentration plus A minus concentration giving our total weak acid, which is nothing more than a conservation of mass formulation. And then our 2 CO2 equations. The first one, hydrogen ion concentration times bicarbonate ion concentration, which is in equilibrium with partial pressure of CO2. And hydrogen ion concentration times carbonate ion concentration in equilibrium with bicarbonate ion. These 6 equations are really Stewart's model. Certainly it's possible to introduce many more equilibria for each new weak acid or base added, but this is a simplified model from which we derive all of our understanding. Again, I'd like to point out that solving this equation is not the point of this course. The solution is actually a 4th order polynomial in H+, but I'm not even going to show it here. What's important is that you understand the origin of the 6 simultaneous conditions, which then give rise to 6 simultaneous equations. We'll leave their solution to the computer. However, once we have a solution, we're able to get very valuable graphical information about how this all behaves. Let's first look at a graph of hydrogen ion concentration as a function of partial pressure of carbon dioxide, where we have chosen a fixed weak acid concentration represented by our total plasma proteins of 70 grams per liter. You may choose to use millimeters of mercury or the kilopascal scale for partial pressures of CO2. Both are shown on the graph. And also, the pH scale appears on the right-hand side if you prefer to think in pH terms rather than hydrogen ion concentration. Let's sweep carbon dioxide from a very low value, hyperventilation, through the typical arterial blood levels all the way up to respiratory failure, in other words, very high values of CO2. For this curve, we fix the SID at a very low value of 20 millimoles per litre. Notice how as CO2 increases, so does the hydrogen ion concentration. Next, we jump to an SID of 25 millimoles per litre. And as you see, the hydrogen ion concentration increases with CO2, as before, but at lower values now that the SID is more positive. We repeat this with higher and higher SID values, with the curve somewhere in the middle being an SID of 40 millimoles per litre, which is approximately normal. As our SIDs pass this point, we get lower and lower hydrogen ion concentrations, although still always increasing with carbon dioxide. We can now examine curves by fixing SID at 42 millimoles per litre, which is a typical physiological value, and changing the weak acid concentration in this case, in other words, the plasma proteins. We start with a very low plasma protein value of 20 grams per litre, and as you see again, the hydrogen ion concentration increases with increasing carbon dioxide. Or, if you like, if you look at the right-hand curve, the pH drops with increasing carbon dioxide. However, as we increase our plasma proteins, in other words, our weak acids, each successive curve produces higher and higher hydrogen ion concentrations for a given level of CO2. These curves summarize acid-base balance. Notice how hydrogen ion concentration is dependent on weak acids, CO2, and strong ions.